Today we're going to do Introduction to Sequences. And so some of you have seen sequences in Algebra 2 and some of you have not. So I wanted to go through some helpful vocabulary first. So this vocabulary list is in your notes for you to refer back to. But first, a sequence. All it is a function, except its domain is the set of positive integers. So that just means it's a function, but I can't plug in the number 0.5. So an integer starts at 0 and goes up 1, 2, 3, 4, 5 and down -1, -2, -3. This is only the positive integers, so I can only be 1, 2, 3, 4, 5 and up. A sequence is usually represented by listing its values in order. The terms are just the ordered list of numbers in the sequence, so we're going to be using the word terms a lot. An infinite sequence goes on forever, so it's a sequence that never ends, and it's usually indicated by ... after the last term, whereas a finite sequence only has a fixed number of terms. So infinite versus finite is going to become important when we start later in this unit talking about series, because series are adding up the terms of a sequence. If it goes on forever, how can you add up all the terms? We're going to talk about closed versus recursive form today. So closed is also called explicit form, but it's a formula that allows direct computation of any term in the sequence. So if I want to know the 10th term, bam, I plug in 10 and get an answer, just like a function. Recursive form, however, is a formula in which each term is defined as a function of the preceding term or terms. So if I want the 10th term, I also have to know the 9th term, the 8th term, the 7th term, and so on, all the way back to the beginning. So recursive is not quite as useful, but there are some functions that can only be defined recursively, and one of those is the Fibonacci sequence that you might have heard of. A sub n is just a notation, and it helps us distinguish between a function and a sequence. So we're going to use a sub n a lot today. So the function f of x equals 3x minus 2 has a domain of all real numbers, but the sequence a sub n equals 3n minus 2 only has a domain of the positive integers. 3x minus 2, 3n minus 2. It's the same function. I can just only plug in 1, 2, 3, 4, 5 here. I can plug in whatever I want up here. A half, -3. When graphing terms of the sequence, the points should not be connected because there's no value between each term. Like I just said, I can only plug in 1, then 2, then 3. I can't plug in 1.5. So I'm not going to connect whatever the first point is to the second point. I'm just going to leave them as points like a scatter plot. So those definitions you're going to hear a lot, but they're up there for you. All right, so here is some function notation, sequence notation. So we're going to practice just writing the first 4 terms for each sequence. So what that means is you're going to first plug in when n is 1. So when n is 1, I get -1 to the first power up top, so that's just -1. And then I get 2 times 1 minus 1 on the bottom. So 2 minus 1 is just 1. So when I divide -1 by 1, I get -1 as my first term. Now let's plug in 2. What is -1 squared? -1 times -1 is +1 this time, and I'm going to plug in 2 in the bottom. 2 times 2 is 4, minus 1 is 3. So my second term is 1/3. Now I'm going to plug in 3. -1 cubed is -1 again. I'm going to plug in 3. 2 times 3 is 6, minus 1 is 5. So my next term is -1/5. My last term, can you guess what's going to happen? Negative, positive, negative. It's going to be positive because -1 to the 4th power is +1. I'm plugging in 4. 2 times 4 is 8, minus 1 is 7, positive 1/7. So -1, positive 1/3, -1/5, positive 1/7. So you notice that when you raise -1 to even and odd powers, you get that alternating positive and negative pattern. All right, now I'm going to plug in 1, 2, 3, 4 for this n, just like you would plug it in for x in a function. If I plug in 1, I get 3 plus -1, and 3 plus -1 is 2. Now what happens when I plug in 2 up here? -1 squared is +1, so I'd have 3 plus +1, which is 4. Now I'm going to plug in an odd number again, -1 cubed. So 3 minus 1 is back down to 2. Can you guess the next term of the pattern? When I raise this to the 4th power, I get +1 again. 3 plus 1 is 4. 2, 4, 2, 4. Number 3. When I plug in 1, 3 times 1 is 3. Minus 2 would be 1. All right, now when I plug in, I'm going to have to plot this over here. So actually, I'm going to list these. When n is 1, I get 1. When n is 2, when n is 3, when n is 4, because it's kind of like a coordinate, 1, comma 1. 2, when I plug in 2, I get 6 minus 2 is 4. So I really get 1, comma 1, 2, comma 4, 3, comma 9 minus 2 is 7. Plug in 4, 12 minus 2 is 10. So I get 1, 1, 2, comma 4, 3, comma 7, and 4, comma 10. So it's just a straight line, right? It would have a y-intercept at -2, slope of 3, but I'm not going to connect the dots because it's a sequence, so I just have those distinct points. So that's the first thing you have to be able to do, is just generate terms of a sequence. It's just like plugging in x, except you're plugging in numbers for n. If you want the first 4 terms, you're going to plug in 1, 2, 3, 4. Plug in 1, 2, 3, 4. Plug in 1, 2, 3, 4. All right, so the second thing to just be familiar with, just kind of good to know in math, listing a couple terms does not define a sequence. You must be able to write the terms of the sequence like a formula. So it's like writing out the function. It can be difficult. I'm not going to have you do it a lot. I'm not focusing on sequences. This is pre-calculus. We're actually going to be focusing on series. But to get to series, we need an understanding of sequences. So I just wanted to introduce to you the idea of finite differences. They can help us determine what degree function might best be used. This will only help us when it's linear, quadratic, cubic, so polynomial. It won't help us with square root or exponential. So I just wanted to show you how finite differences work. So as long as these are terms in order, right, the first term, the second term, the third term, and so on, a finite difference asks you how far of a difference is it between each of these numbers. 4 to 9, that's a jump of 5. 9 to 14, also a jump of 5. 14 to 19, also 5. 19 to 24, also 5. If these come out the same, this is called a first order finite difference. It's because we just did it one time, right? So we found the difference one time. They came out the same. That just tells us that this is a linear function. So if I was doing a regression on my calculator, this would be a scatter plot. That would be a straight line. I would want to do a linear regression. Let's look at a different example. 5 to 8 has a difference of 3. 8 to 12, 4. 12 to 17, 5. And 17 to 23, 6. Did that come out the same? No. That's the first order. This is called the second order finite difference. 1, 1, 1. Did that come out the same? Yes, it did. Second order finite difference can be represented by a quadratic function. So if you were going to look at a scatter plot at this, of this set of data or this pattern, it would come out as a quadratic. What do you think my next one's going to be? Can you predict? So this is going up by 7, up by 19. See, I don't want to make a mistake here. So, oops, my battery's running low. 56 minus 19 is 37. 117 minus 56 is 61. Did that come out the same? Nope. Let's see. 12, 18, 24. Did it come out the same? Nope. How about now? Third order came out the same. It'd be nice if there'd been a little bit more data here, but we got 2 6s. So cubic function. So however far down you have to go to find a pattern of differences that are the same tells you the degree of the function. But like I said, it only works some of the time, and it's not going to be a big focus, but it's something you might not have seen in Algebra 2 that is kind of useful. Okay, let's talk a little bit about recursive sequences. These are not as useful, but there are some sequences that can only be written recursively. When writing recursive sequences, sometimes you might see a sub k, sometimes it'll just be a sub n. So here's the Fibonacci sequence. We're going to look at some videos about the Fibonacci sequence. It's kind of a cool sequence. 1, 1, 2, 3, 5, 8. What's the pattern? So the pattern for Fibonacci is that you take the first 2 terms, add them together to get the second term or third term. Then you take the next 2 terms, 1 plus 2 to get 3, 2 plus 3 to get 5, 3 plus 5 to get 8, and so on. The next term would be 13 because 5 plus 8 is 13. So it's just to add the 2 preceding terms. How would this be written using a sub k notation? All right, I'm going to tell someone how to get the next term. Take the term before it and add the term that came before it. So you're not actually plugging in anything here for k. A sub k is a placeholder of order. So if a sub k is right here, let's say that's a sub 7. The next term is a sub k plus 1. So if this was term 7, this would be just term 8. K plus 2 comes next. That would be like term 9. What if we went backwards? A sub k minus 1 would come before it. So I'm just pretending if this was the 7th term, 7 minus 1, this would be a sub 6, the 6th term. Or k minus 2, the 5th term. What if this was 100? Then this would be the 99th term and the 98th term. You're not plugging anything in. This is like reading a story. It tells you to take the term that came before it and add the term that came before that. So here I am, take the term that came before it and add the term that came before that. Example 2. Here, something important for any recursive sequence, you have to tell the person reading this either the first and second term or just where to start. If this is the sequence, you have to take 1 as the first term and 1 as the second term. So then 1 plus 1 would make 2 and so on. So you have to tell them where to start. That's very important for recursive. See how over here they tell you, hey, the first term is 3. Well, great. How do I find the next terms? Read the story. K plus 1 in order would be here. A sub k just refers to the term that comes before it. So if 3 is the first term, what does it say to do to 3? It says to subtract 2. 3 minus 2 is 1. Now it says, okay, whatever term you're on, just subtract 2. 1 minus 2 is negative 1, and then negative 3. So I found the next 3 terms of the sequence. How about this one? Okay, my first term is negative 3. What does it want me to do this time? It's telling me to find a sub k. I'm here. Do what? Multiply the term before it times 2. Negative 6, negative 12, negative 24. So I'm just multiplying by 2 each time. It's like reading a story. I'm not really plugging things into the formula itself. A sub k is just representing term order. Okay, so a little bit about recursive sequences in case you've never seen them before. The last thing I wanted to catch some of you up on, if you've never taken statistics, there's something called a factorial. All that a factorial is, it's represented by an exclamation mark on your calculator. It's the product of the integer and all the positive integers below it. We define 0 factorial as 1. 1 factorial is just itself, 1. 2 factorial means take 2, multiply by the integer that came before it, and 2 times 1 is 2. To find 3 factorial, take 3, multiply by 2, and then multiply by 1, so 3 factorial would be 6. I want to show you where that is on your calculator. It is under, not stat, Oh, it's under math, and then all the way over to probability. So math prob for probability. There's your exclamation mark under number 4. So it's under math probability number 4 on the calculator. All right, this one I can do without a calculator. 11 factorial is going to be 11 times 10 times 9 times 8 all the way down to 1. 10 factorial is going to be 10 times 9 times 8 all the way down to 1. Guess what? All those are going to cancel and give you 1. What are you going to have left? 11 in the numerator. So the answer would just be 11. Number 2, I am going to use a calculator run. I'm going to take 20 factorial and divide by parentheses 10 factorial times 8 factorial, because 9 minus 1 is 8. 20 math, there we go, divided by, what am I doing? 10 factorial and probability times 8 math ability, close parentheses. 20 factorial was a pretty big number, so even though I divided by a pretty big number, I still got a pretty big number. Let's see, looks like, is that 16 million? 16,628,040 comes out to my answer on the calculator. Number 3, you really could do this without a calculator, or you could just do 8 times 7 times 6 times 5 times 4, right? Because 3, 2, 1 is going to cancel with the 3, 2, 1 in the denominator. So if you don't want to find the math prob factorial key, 8 times 7 times 6 times 5 times 4, 6,720. What about a sequence that involves a factorial? Find the first 3 terms of the sequences. Well, 2 squared is going to give me 4 in the numerator every time. And then the denominator is just n factorial. So 1 factorial we said was 1, 2 factorial we said was 2, and 3 factorial we said was 6. So 4, 2, and 2/3 would be the first 3 terms of the sequence. All right, well, n factorial we just did over here. It was 1, 2, 6. So 1, 2, 6 is my numerator. N is 1, 2, and then 3 in the denominator. So 1, 1, and 2 would be the first 3 terms of that sequence. So just a lot of little bits and pieces that are going to be helpful to you this unit. You are going to try this next page 1 through 10, the guided practice. Let me know if you have questions, and you should be posting that 1-page guided practice in Google Classroom. Thanks.